Thank you. It's a great pleasure to be here and to honor Richard, who I've known for a little more than 50 years. So to prevent using up all my time, I'm going to just plunge in right away. And the subtitle of my talk is Some Answers to Difficult, Improbable, and at times Impossible Questions. And I do say often that my paleontological and anthropological colleagues often ask impossible questions. And I'll just give an example of one that I'll return to in the talk. Somebody at Olduvai Gorge handed me a stone tool and said to me, well, was the hominin who made this tool sitting in the shade when he made this tool? And so there's an example of an impossible question. But later in this talk, I'll demonstrate that we at least figured out how to quantify shade on the landscape. And my answer to him at the time was, if you tell me the time of day, I can tell you if he was sitting in the shade, and also show you some data that would suggest that we can, if he could tell me the time of day, that yes, we could decide whether or not he was in the shade or not. Richard is the real acknowledgement here, but you'll notice there's a big long list of other people that, and at the end, and many others that I have to acknowledge that I've collaborated with over the many, many years in East Africa. And all of those people I started working with because of Richard. So he has so greatly influenced my career. And almost all the scientific colleagues I've made in my career resulted from the work that I started up there so many years ago. That's me in 1971. I was a draftsman in the geology department at Iowa State University. And Karl Vondra came in looking for a guy named Albert Plug. He says, where's Verplug? And Verplug says, I'm over here. And Vondra said, well, I need somebody to go to Africa to map this summer. Jim Richardson can't go. And Verplug looks at him and says, well, Dr. Vondra, who is notably cheap, said, I need a paying job this summer because I want to buy a car. And so I said, I'll go. And a month later, I'm in Africa, having flown my first airplane ride ever, and working on the geology of Turkana Basin. Well, what was it like? Oh, let's go back a little bit. This is the basin size, and I put in, for exactly the same scale, much of Greater New England. I want you to imagine on the right-hand side, if we could put a gas station, or put a red dot on every single gas station, that entire field would be full, whereas there would only be one on the left side. And it was Richard who provided the logistics. And then following the TBI, it's the logistics that allowed us to do things, because it literally, you could not do that on your own those days. And of course, it takes 3 days to get from one side to the other, whereas I think it takes less time of that in Massachusetts and New Hampshire and so on. The other important thing to consider, especially when those of us working on it were criticized for taking so long. I mean, it took Dick Hay only 10 years to do Olduvai. Well, there's Olduvai down there, and here's Hadar, Gona, Dakika, Middle Awash, and here's Turkana Basin. It's an enormous basin. So not only the logistical difficulties, it is darn big. In 1971, we had these maps to go by. Up here is a mountain peak called Baracini, which in the Gala language, going back to, until we found a Gala Italian dictionary, and Baracini means, you mean that over there? So, so there we have it. And the geology is nicely mapped here. And yeah, that's where we were in 1971. But the year before, Richard had arranged Huntington to make some detailed air photos. So we had these air photos, but of course these were not pegged into the GPS system, which was going to be invented 20 years later. But we had good overlap. And so this is what we had to work with. And Ian Findlater and Bruce Bowen, who I was working with, and me and Bob Reynolds and some others, the Iowa State crew, were able to construct some maps. So here's the Kubi-Thure area published in 1975. So that was really probably the status as of perhaps 1972 or 1973, and a little bit of stratigraphy shown up there in the corner. Where are we now in 2023? I just want to mention that we got to fix some things first, because things we were learning as we were going, and it, as I said, is a really big area. So issues of chronology, how old? Craig Feibel went over a bit of this, but we have these volcanic events. They are expressed in Trachana as volcanic ash layers. And the KBS story in one slide has two important things to see. Is the very first really estimate was 2.61. Now remember that this is less than 10 years after the very first potassium argon dates were published. So you all are now using techniques that are fairly well developed and well established. But in 1969, when Fitch and Miller were making their measurements, that was really absolutely cutting edge. The step heating technique had only been proposed a year before that. And so it's also worth remembering that, we're learning how to use these techniques. Garnis Curtis, I was an undergraduate student by then, and we're working with Garnis Curtis. And so in 1975, we published an age of 1.82, plus or minus 40,000 years. And so, oops, that makes man 500,000 or almost 1 million years younger. And so that did get everybody upset. And that's a time for a different conference and a different story and all of that. Ian McDougall was invited to settle the controversy. I do think Garnis got a bit of a short stick on that. But notice that the first dates of Fitch and Miller were plus or minus 260,000 years. Garnis's date in 1975 was plus or minus 40,000 years. McDougall and Brown, 1986, essentially the same age, a little bit older, plus or minus 21,000 years. So Dave Phillips now, based on new instruments, better blanks, we're down now to less than plus or minus 1,000 years. So now we're within a precessional cycle. Okay, the precessional cycles are 20,000 years, and now we can find out where we are within precessional cycles. So this is an extremely exciting advance, and we're going to see in the next few years incredibly better precision. The other thing that's important to remember is one of the persons who I filled up that little bottle there on the left-hand side with all those little tiny feldspars. And early on, and I did the mineral separations for some of Garnis's things, we had to have that much material in analyzed to make an analysis. And one pre-Cambrian grain in there would throw us off considerably. So, possibility with Fitch and Miller is that they had a little bit of stuff that shouldn't have been there. So now we can date just a single one of those little tiny grains sitting down there below the pumice sample. The other problem was correlation, what goes with what. This was the stratigraphy estimated as of 1975, and so you can see 5 things that we were following around, maybe 6 or 7. There's the 3.9 and 4.5 tufts, whatever those things are at the bottom. We had this Sergei thing that, as Craig pointed out, is a diatomite, Tulabor tuff, just below the KBS, and so on. We need to do some trace element and chemistry. And actually, we found early on that by actually physically looking at some of these volcanic ashes, we could actually physically see that, oh, these were, the Thure had a bunch of different, was different in different places. So we knew very early on there was problems. And working with Frank Brown, we were able to find out that yes, there's, we could correlate things to the Shungura, and oops here, big problem, Thure tuff in the original stratigraphy actually isn't Thure tuff at all. It's a different tuff, and Thure tuff is way, way down here, much different age than the thing called the Thure tuff in Area 102. So many more tuffs, and more than 150 tuffs. Craig yesterday said 300 tuffs. My 150 is 150 useful tuffs, and then there's still another 100 plus not so useful tuffs that we seem to have found only in a single place. So just a very different situation. But what is exciting is this is the most securely dated terrestrial section in the world. And all of those little dots on the left-hand side of the dating, along the dating scale, are ages of some sort. So this is an incredibly well-dated sequence to study evolution and other things. In the marine records, perhaps we have better dated sequences, but nothing in any continental area in the world works like this. And these correlations can be used to other sites. They can be used to date other sites. Tuffs from Turkana Basin have been found in the Baringo Basin, in the Albertine Rift, in the deep sea, and so on. So this is, and some of that work is continuing in spite of Frank's death. Maps, where are we? I showed you, some things that we had. This is a beautiful map that Bob Reynolds has put together in the www.turkanastratigraphy.org. What Bob has compiled is on this website is just absolutely phenomenal. And if that's not phenomenal enough, you can actually put it on your cell phone and it show you where you are in the field. And so what we have is not only the member maps up at the top here, but then an age map that Bob has split out the ages, because there's many marker horizons within the individual individual members. So fantastic improvement in things over the last few years, and frankly, I really envy the people who have to do that, because I really did not find the mapping very much fun, and perhaps that's the reason why Richard recognized this and invited Frank to do it, and allowed me an exit from the mapping and correlation project, which is what I did. All right. I mentioned one of the impossible questions that I was asked. Well, these are the questions that we want to know. What kind of vegetation is there? Is there seasonality? Is there migration? How hot is it? How dry? There's all of these questions that need to be answered. And frankly, in 1971, there were not any methods for doing these. You basically say, well, let's use fossils. Fossils will tell us what those environments are. The rest of my talk is a little bit using fossils, but using your brain as well. So Bernard Wood gave us an important thing to think about. So I'm just going to say, once you find those keys under the lamppost, be sure you know how to drive, okay? And what are the rules of the road? So I'm going to talk about some of those issues, because if you don't know how to drive, maybe you'll just follow that sign, and it's going to be an unhappy thing. All right. Turkana Basin really has been a proving ground for developing terrestrial paleoenvironmental indicators. I think that's, we just have to admit, we've learned so much here. I'm going to start out with going back to this shade question and then get into some other things. And in the carbon isotope ecology in the tropics is wonderful because we have these C3 and C4 plants which have the different carbon isotope ratios. And on the right side, the right side, your right side, we have the tropical grasses, are these guys. And over here we have trees, shrubs, and herbs. And here's sort of two examples of a pure C3 ecosystem and a pure C4 ecosystem. Nice isotope distinctions if we can figure out how to use it. So can we quantify shade? Well, here's a bunch of examples. This doesn't go quite where I want it to. So there's almost 100% open. This 21% woody cover. Yeah, we think back to our math days and redefine variables is the way I like to think of this. So we redefine our variable shade. We'll redefine that as woody cover. And woody cover is something we can quantify. It's difficult to quantify shade, but wherever there is woody cover, there is shade. So we're just going to say woody cover is really shade. And here's a nice place that's 99% shade. It's only this road that's been punched through that is the little 1% that's not shade. So this woody cover could be an indication of ecosystem structure. So we worked on that for a while, but remembering that trees and shrubs are shade and the herbs are not shade. So we have both C4 grasses as not shade, and we have herbs as not shade. So, you know, the little cucumbers growing out in the field in Turkana, those are herbs in our C3 plants. So we do have to take into account of that, but we can go around and look at modern ecosystems. And again, here, jumping ahead of myself, I have to thank Richard, because it's Richard who introduced me to the key people in the Kenya Wildlife Service. And so we were able to use all the national parks and national reserves in Kenya to study modern soils. So we find, and in those places, we're able to quantify shade and not shade. And there's our 1% site, and there's our 1% site. And that bush there is that bush up there. And this is in Samburu, and we're taking a picture from right about here, looking up in that direction. So here's a sense of what those environments look like in terms of shade and not shade. And we use these differences in color density to determine the shade composition. And so we can make a probability function based on about 100 soils that we looked at from around the world, from tropics and semi-tropical areas, and use the carbon isotopes to give us a probability estimate of the fraction of woody cover. And so I started this work actually about the time that I kind of exited the mapping correlation business, and have been working on soils as indicators of paleoenvironments. And so this is a figure that we've already seen in one of the talks that we produced some years ago, but shows the difference between the Shungura, which is near the axial drainage. It has a lot more shade than the more distal parts of the basin. And if we can stick in a couple of hominins, we can actually say that, wow, these individuals were living in something more like this. Definitely not that, and certainly not open grasslands, but something intermediate. And one of the problems, I'll just make a comment here with the savanna hypothesis, is that everybody defines savannas differently. And the way that savannas are defined is just a discontinuous, semi-continuous tree cover with grasses. So a pure grassland is not a savanna, but you can get actually savannas with up to 75% tree cover in Australia. So we've been able to do shade, and this is Inke Nagash has updated this and has a paper, hopefully, well, not quite in press, but certainly in review, at this point on reevaluating this, and that'll be coming out soon. So we can quantify things like shade. Oh my, I'm running out of time. Oh no, I get more time because I'm a special. How hot? How hot? Well, this has always been a question, and golly, how does one answer this? Well, you know, one way is to say, well, we have laterites, and so we know they're really hot and steamy. We don't have glaciers, so it must not have been cold. That was in 1971 about what you could do for terrestrial environments and how hot it used to be. Or you could say, well, the animals are going to tell us something. But how hot is a real tricky one. So this is the problem. Nakuru is a nice, God, what a nice spot to be a rhinoceros or something. Mean annual temperature is 7 degrees Celsius. Turkana officially is used to be 29 degrees C, but actually is even hotter today. And Ben Passy a few years ago put together this nice diagram taking just different chunks of the whole entire planet, and you find that Turkana is in the top percentile, whatever temperature increment it is. It literally is one of the hottest places in the world in terms of mean annual temperature, and I challenge anyone here to actually find a weather station that has lasted longer than 10 years that's hotter than Lake Turkana. There are a few, but very, very few, and they are all of those are in this little tiny box, okay? So where we are here, that's, you know, we're nice right in the middle of the planet for coolness. So how do we do temperature? Geologically, this was the transformation in the beginning of stable isotope geochemistry, was this reaction that Harold Urey presented some years ago. And what you have is a oxygen, the light oxygen is in the carbonate here, a heavy oxygen in water, and then, oh, look, now we've got one of the heavy oxygens in the carbonate, and the water is full of the light oxygen. And this really, you all remember, I'm very sure, from when you were in 4th grade and took chemistry class, all chemical reactions are functions of temperature. All chemical reactions. So if you have an equilibrium chemical reaction, it is a thermometer, if you can figure it out. So this sort of really transformed geology, as we finally had a thermometer. Harold Urey thought he was just doing calculations with partition functions, and he found he had a thermometer. And so the thermometer is, you need to know the isotope ratio in calcite, which we can measure, and you need to know the isotope ratio of water. Well, we can measure the ratio in calcite, and the reason it works in the marine environment is because the ocean isotope ratio of water is almost constant. And the other thing that helps us out, Nick Shackleton pointed this out, is, well, the bottom water is very close to zero at all times. And so if you take the benthics, which grow at the surface, and, the planktonics, which grow at the surface, and the benthics that grow deep, and compare them, you can deconvolve the whole thing. So that works great in the marine environment, but in the terrestrial environment, we have such a range in the isotope value of waters. In Lake Turkana alone, I've measured a range in isotope delta-18 values of almost 20 per mil between the most evaporated waters and some rainwaters, and that corresponds to a temperature range of 80 degrees Celsius. So even saying, well, we're going to eliminate the odd, really evaporated ones and the very unevaporated ones, we still have we cannot use calcite as a thermometer with this traditional method. So about a little more than 10 years ago, John Eiler at Caltech said, well, let's do something else. Let's write a chemical reaction. So this is my favorite chemical reaction. And we have these mineralogy students, and one of our faculty members always has a weekly quiz as to of these minerals, which is your favorite minerals? And then she does this at the end of the year. And I always say my favorite mineral is calcite. It is the greatest mineral because you can do so much with it. And look at this. If you take calcite and you react it with calcite, you make calcite plus calcite. Phenomenally. What a great reaction. Wow. And then in more detail, you just keep track of these little labels, okay? And the key is that there's a heavy carbon coupled to a heavy oxygen. So can we do that? And this is called the clumped isotope methods. So we only need calcite. It's independent of water. The only problem is you need 2 more decimal places to what we did traditionally. So John Euler said, okay, I'm patient, I'm gonna wait a long time. And so what you need is patient geochemists, and one's good with their hands. The first application of this to paleosols was in the Turkana Basin by my student Ben Passy and Naomi Levin. And if you want to, another one of my students, Will Mace, buried a bunch of soil temperature probes all over Kenya. And this is the sort of thing. Now, if we couple this with the paleo shade indicator, this is what we're going to be able to get out. So, in the open grassland, this
happens to be in Meru National Park. This is for 3 months of the year, June, July, August, the average temperature with the uncertainty envelopes for the ground surface temperature. So imagine you're a hominid, this is what your feet are going to encounter. Or if you're one of Dino's ants walking around on the surface, okay? This is an astonishingly average, daily average high of 55 degrees Celsius. At Lake Turkana, this is actually 70 degrees Celsius. So those high-stepping ants that Dino pointed out to me have reason. They're just dancing, okay? But in the shade, in the riparian forest, we are just a nice, comfortable degrees. So if you can tell me the time of day, and I've got my isotope thing telling me what the woody cover was, I can tell you which one of these curves that you were on. And if you're actually in this curve, you're in the shade. If you're in the top curve, well, this is in the shade because the Earth is shading us until 6 o'clock in the morning. You only have about 2 hours in the morning when you're going to likely be out in the sun. But if you just watch goats, you can see up at Turkana, the goats are in the shade, starting about 9 o'clock in the morning, and they're pretty much in the shade until they get herded home. I think if hominins were as smart as goats, they'll have been in the shade for almost the entire day up at Lake Turkana. Only geologists and archaeologists are out wandering around, and anthropologists. So, if you really want to find out about this, come back in a little while, and Greg is going to tell you how it really works. And I'll have to take off my hat to his advisor Ben Passy and to Greg himself. It takes incredibly patience. You have really careful measurements. This is got to go to take a lot of driving lessons to do this properly. What did animals eat? That's another important question. Well, the analogy is, animals in the past, they did exactly the same as animals today, and so that's what they did. Elephants ate what they eat now, and hippos ate what they eat now, and everybody eats what they eat now. In 1989, Richard Leakey was appointed to the head of Kenya Wildlife Service. Turns out this has an incredibly important thing, and that paleo shade indicator was developed because Richard encouraged me to talk to the right people at KWS, and I made these wonderful contacts that have lasted several decades for working with some of the park's people. The same year, we heard about Bob Brain
yesterday, the day before, but Julia Lee Thorpe in this audience here published a most astonishing paper with Bob Brain that showed that 2 different monkeys in the fossil record had different isotope values. To me, this said, oh, okay, these things work. So this is a fantastic revelation, and Julia and I both will commiserate if you give us enough wine or beer or something, and about how hard it was to convince the community that tooth enamel is not the same as bone. And if you're a young person and want to do isotopes, just don't do anything with fossil bone and oxygen and carbon isotopes. Just go away. But enamel is a wonderful substance. We applied this to some paleosols in Pakistan right away, kind of to help prove that the method worked. And what we found was that we had, in Pakistan, this gray line is the average delta C13 value of paleosols. So we went from a C3 ecosystem to a C4 ecosystem. So, okay, we're going to prove those people right that they've got to believe us because it turns out that when the ecosystem shifts in Pakistan, the diets shift. The animals found, they found this new restaurant opened up and they went to it and took advantage of this good resource. And at the same time, we thought, well, this gives us a great opportunity to prove the long-standing horse controversy, not controversy, but idea that when equid teeth got taller, it was because they started eating grasses. And what kind of grasses? I'd ask the paleontologists. They'd say, well, the same ones as today. Well, in America, they're eating C4 grasses. So we thought, well, great. We can show that we know stuff because we'll prove that Gaylord Simpson's was right. And what we found is, oops, in the diet switch in North America was the same time as the diet switch in Pakistan. Wow, this has got to be a global thing because, animals weren't talking to each other and telling each other that, oh, there's this new food that's been around that nobody pays attention to. No, if it's there, somebody's going to eat it. And Kevin asked this question. So a little bit before this paper was published, because we were collecting this data, I wrote to Meave and I said, Meave, if you can give me your collecting team and we'll work on stuff that is so lousy you won't even collect it in the field. Give me that team for a couple of days up at Lothegem, and I'm going to give you the best Christmas present you ever had. And so she did, and I think I gave her I don't know about her Christmas presents, but I do know that it was pretty darn good because I was able to send back stable isotope data from Lothegem that showed that we could do diet, and there were some really surprising things. So I'm going to just back up here a second. Some of the things were so surprising that we had to start working on modern ecosystems. So at some point I said to Richard, nobody has done this sort of thing on modern animals. What can we do? And he says, well, what you do is you go talk to this person and this person and this person, KWS, and I'll make sure that you get a research permit, and we could actually work in every single national park in Kenya, which is really fabulous. And so we started, and for me, what I found is that this is a real interesting playground, and so this has led to a whole series of papers on bovids, on elephants, on hippos, on rhinos, and all sorts of things, and led me into a series of deep collaborations with many people, including, as it's shown sort of on here, even into isotope forensics. So we're working with confiscated ivory. But it was this start that was so wonderful and helpful to me. But it meant what we found out was that, well, actually some of the guidebooks weren't right. And what the guidebooks said animals ate, which people depended on, wasn't what most animals actually ate. And it was often you trace back things like elephant diets or hippo diets. Those all trace back to one massive culling site in Uganda that was done because the park was overpopulated. And so that, we've only, at the time, hippos were pure grazers according to the literature. Well, turns out we've done lots and lots of hippos. We found 2 pure grazers. One is at Lake Turkana, and one was one of the animals that was killed in the cull from Queen Elizabeth Park. Queen Elizabeth Park hippos have a completely different diet than they did in the 60s when this cull took place. They have completely changed their diet. So we can also apply this to other things. One of the really interesting things are these darn elephants. And the important key here is modern elephant diets. Loxodonta is here. Oh, look at, and all of the fossils are grazers. So, and Dinotheres, those aren't elephants, those are Dinotheres. Dinotheres are over happily in the browsing space, but fossil Loxodonta, we early found on was a grazer, and Elephas was a grazer, and it's still that way. And now we've pushed down fossil grazing elephants to Chalo's site at Notre Dame at 230,000 years, and the first browsing elephant was collected by Marta and is 130,000 years. So the modern elephants have a completely different diet than what we have for most of the fossil record. And what this means to ecology needs to be evaluated. The ecologists say, oh, these are the keystone species and the savannas are the way they are because of elephants, among other things. Well, elephants, for millions of years, were not doing what elephants today do. Some other things that we were able to do is just look at, in this case, this is just tooth length versus delta C13, and we can see in Nyanzacurus, Notacurus lineage, we can actually document this change in diet. And so there's actually a number of taxa who have changed diets during the course of the Turkana sequence that we have. Not only to the change in C3 or C4 abundance at 7 million years, but throughout time. So we have a grazing giraffe, Shivapithecus, gets shorter and begins to graze. Some other things that we can do is look at it at the ecosystem level, and Jason had a slide similar to that. What's significant is if we look at modern APP means artiodactyls, parasitactyls, and proboscideans, excluding little tiny ones that are often not collected. But we can lump these together. Are these grazers, mixed feeders, or browsers? And significantly, at 4 million years ago, we seem to have ecosystems. We haven't found any ecosystems that are in equivalent space. And that's interesting. What ecosystem really was that? So other important questions, but provides an illustration of the way that isotopes can do some different things. Hominid diets. Well, that's for Julia. Julia's going to talk about that because I don't have time. What else we got? Seasonality. A number of people have brought that up. Seasonality is related to migration. What is seasonality? Well, here is a really interesting problem, and I suggest you take some driving lessons. Okay? What we find with hippos, this was a project that Ben Passy did for his actually master's thesis. Well, he found that the maturity of enamel takes, in the case of a hippo, about 60 millimeters of time. That's about 1 year to 2 years of growth. So it takes a while, and so it starts out only as 20% mature, and so it's got 80% overprint. So if you want to get diet, you've got to realize that you're not looking at a single diet. Here's the hippo model. We can take, this is actually an isotope record that has been measured in somewhere, and we make it into a hippo enamel using what we understand. That's what that signal would look like. And then we have to take math. And so we I just say to people, make friends with a geophysicist. They love this kind of stuff. So you can, if you have the right parameters, you can make this back into the input signal, okay? And that method is called inversion. Here's just an example that we did where we actually, it was a controlled diet, and we have the breasts, so we know what the animal was eating. That's these dots down here. And we told it to eat C4, but it didn't like it, so that's why that little dip is there. And if we actually model the enamel, we see that actually the change shows up technically before it actually occurs, but that's because that's overprint. So all of this part that's above this baseline is the overprinting part of the signal. All right, so now we need to invert this method, and with the inversion method that Ben developed, oh, look at this. We get this square wave back out. You don't get square waves by accident on the output of mathematics. So we have mathematical methods to unmix these complicated signals. This is just one example of a hippo that we know died during a drought, and carbon isotopes. The dots represent the data. Now look at this gradual carbon decline, and oxygen, sort of a gradual increase. But the inversion method shows that it's essentially constant with some variation, but a diet crash, okay? So there's a very abrupt diet crash. So the important thing on these sequential sequences is that the amplitude is different and the shape is often different. It's actually a different signal. It's not just an accordion that you can make interesting music with. Well, you will make interesting music, but it'll be wrong music. So, how dry? Just quickly, Naomi first came up with the idea of an aridity index, and so what we know in isotopes is oxygen isotopes evaporate, so the difference between a meteoric water and evaporation should give us that. Well, we don't have any water. Well, maybe we do have a little bit of water, and that water is called a hippopotamus. So you simply need to subtract a hippopotamus from a giraffe. It's difficult to do, but it's easier in isotope space. Okay, so here's our first aridity index, is subtracting a hippo from a hippopotamus, and we see that we have a paleoaridity index. The problem, like with the carbon isotopes, is we need to know that those two animals were living at the same time. If they're 20,000 years apart, we're one precession cycle apart, and we're in trouble. So this is a good idea, but here's a nicer one because we can do everything in a single specimen. And this is using the oxygen 17 isotope, which I think Greg Henke's is going to mention in a little bit. But oxygen 17 is an indicator of metabolism. And if the oxygen isotope composition in the atmosphere is bonkers. In geology talk, geochemistry talk, we call that the Dole effect. But it's very, very different. And so now we have a tracer for atmospheric oxygen. And it turns out that giraffes make a lot more metabolic water than a hippo does. And so we now have another paleoaridity indicator that we can use. Okay, so we've got lots of things to do now. We've got oxygen 17 in enamel, we've got the delta 47, we've got soils, we can do seasonality and migration, and so for me it's been just sort of a wonderful journey, and I have to especially thank Richard for his many encouragements, but especially on developing the modern analogs so that we can apply these to the fossil record. And in the meantime, we've learned a lot about modern environments. So next decade, incredibly exciting to me. Hydrogen isotopes, especially in biomarkers. Delta C13, lots more diet reconstruction. Carbon isotopes, Kevin mentioned this, really exciting things going on. We can actually detect, past fire histories. Nitrogen isotopes can be trophic levels. It's really difficult. There's not much nitrogen there, but people are working on the methods. Oxygen-17, animal physiology. We can measure animal physiology. Extremely exciting, not only for the fossil record, but actually for modern stuff. We can learn a lot about modern animals. Oxygen-17, paleoaridity or seasonality. Of course, oxygen-18. Calcium-44, the calcium isotopes, indicators of animal physiology. For some reason, Paranthropus boisei is different from all other hominins. What is it in calcium isotopes? Zinc isotopes, strontium-87 with migration. I just want to put in, remember that we often need to learn how to drive, and that's called mathematics and good analytical methods. With dating, we can now get below the precessional cycle plus or minus values. We have a really, really exciting time, and I think if I was a new professor or a graduate student, I'd be looking forward to having a lot of good time working on well, we can't work on all of these, although I got to admit, I've done a pretty good job. Thank you.